This is Gary Rubenstein. I've been teaching math for a long time, at least 25 years, depending on how you count it. I also have two children. One's 9 currently, and one's 12. So I've been watching them go through their math. I'm primarily a high school math teacher, but I've taught middle school, and I've been helping my own children with their elementary school maths. And I thought I'd make this series of videos about as you might be helping your child with math. You might wonder, like, sometimes it's a topic and you're thinking, is this topic really important? Well, sometimes the answer is no. Some topics in math are more important than others for different reasons. What makes a topic important? Well, is it thought-provoking? Does it have trained students to have the kind of mathematical thinking that helps them with math later on? Or is it like a useful thing, like in the real world? Is it a skill that gets used? Or is it just a skill that's going to get used in higher math? So some things are really useful, and some things are less useful. So I made a video, part 1 of this series, where I explained that for kindergarten, 1st and 2nd grade, I'm happy if my child can add and subtract and carry and borrow and do those things. You know, those are all related to the base 10 system. Sort of all implied in there. You know, when you see a number like 222, that first 2 stands for 200, and the second one stands for 20, and the third one stands for 2. And that seems easy to us as adults, but actually that idea is an idea that took thousands of years to develop and be invented. So it's not, you know, sometimes people say that language is kind of hardwired into our brains, but the base 10 number system is not really hardwired into our brain. So it takes some getting used to it and seeing how the numbers mean different things. But when you do understand those things, then you don't have trouble when you're adding. And you say, okay, this is a 70 and a 2, and this is a 30 and a 9, and the 2 plus 9 is 11, but an 11 is a 10 and a 1, so I put the 1 up here with the 10s, and now I add all my 10s together. On the other hand, when I try to do a 7 10s and 2 1s minus 3 10s and 9 1s, well, I can't take away 9 1s from 2 1s, so I trade one of my 10s for 10 1s. This becomes 12. Some people like to just put a little 1 over here. Either way. And I said, for the first 3 years of math, I'm pretty happy if students have a good understanding of this. Now, that's not saying, oh, that's all they should do in math every day is practice adding and subtracting. They could do things like, what's the next number in this pattern? I like that. And just, they can be doing things with money and counting money, adding and subtracting money. There's a lot of things you can do with adding and subtracting. You could do word problems where people are taking things away, eating apples. All those things are good applications of addition and subtraction. Sometimes in the younger grades, they also do some basic geometry, so they learn the shapes, you know, triangle, square, circle. It is good to know those names. They also teach those in preschool nowadays. In 3rd grade, the big skill is multiplication. And the first concept is that multiplication can be performed by repeated adding. So if I say you get 5 cookies a day for 7 days, and if you don't eat any of them, you know, how many will you get altogether? Well, students who've learned adding We'll do it this way. And when they add them up, which they can do a variety of ways, they could add the two 5s in pairs to get 10, get 35. And we tell them that's the same thing as 5 times 7. One thing that's pretty confusing about multiplication is, when you see something like 4 times 5, and we say it's 20, is that 5 4s being added together? Whoops. Because that would equal 20. Or is it 4 5s being added to 20 together? Because both answers become 20. And there's no right answer. Either of those get you the right answer, and they're both the right way. It's not that one is like the right way to think. It's not like this second number is the thing. If I had to choose one, I would probably say that it's more like this. That it's like 4 5s, rather than, I might think of this one as 5 times 4 is 20. But there's not really a rule about which is the proper way to think about it. But it's kind of interesting that these are going to get us the same answer, whether you do 5 4s added together or 4 5s added together. One way to visualize it that students do a lot is they draw a picture. Like a grid that has 4 columns and 5 rows. They make this, it's like a rectangle. And we can see that this, if we counted them all, there would be 20. Now, if I want to say, okay, I'm going to make this first number is going to be the number of circles in each row. Well, the picture would now look like this. And these rectangles, this one and this one, they would have the same number of circles in them. This second one would really just be the first one that's kind of been rotated by 90 degrees. But I think already there's just like a thing in multiplication that's kind of sophisticated. We don't really think of that with adding. When we say that 4 plus 5 is equal to 5 plus 4, we don't really think that much about it. It's like I had 4 apples and someone gave me 5 more, or I had 5 apples and someone gave me 4 more. It seems like obvious that those are going to be the same. But when we do it with multiplication and switch the things around, so it's a little bit more complicated. A question that's kind of interesting to me to ask students is, if I tell you a fact, like I tell you, hey, here's a fact, 4 times 5 is 20. And then I ask, what is 4 times 6? So, well, they could start over from scratch and do 4 plus 4 plus 4 plus 4 plus 4 plus 4, or they can do 6 plus 6 plus 6 plus 6. Or they can take the 4 times 5 that they already know and just add on another 4. So it's kind of like saying 4 times 5 plus 4 times 1. In other words, I have 5 4s, and I'm adding on yet another 4. and I get 24 that way also. I kind of like this idea. It's going to come up in other math, but the idea is if I know something, I'm given something, like I'm told 4 times 5 is 20, you could even go with a bigger question and say, like, if 4 times 35, I tell you that 4 times 35 is 140, and then I say, what's 4 times 36? And you can say, well, if 35 fours together was 140, I just need to add on another 4. And this idea happens in math later also, where there's something that you know so that you don't have to start from scratch to find the next thing. When students start learning the times tables, maybe they run into trouble, like they know that 7 times 5 is 35. But they get confused, they forgot, what's 7 times 6. So a student who knows that multiplication is repeated adding, and that 7 times 5 and 7 times 6 are going to be pretty close to each other, it's just going to be 35 plus another 7, which is 42. Or if you want to know what 7 times 9 is, and you forgot it, maybe you know that 7 times 10 is 70. That's one of the easiest times tables, is multiplying by 10. So I say, well, 7 times 10 is 70, so 70 times 9 is 1 less 7. It's 9 sevens instead of 10 sevens, which is 63. But I like this idea, knowing that multiplication is repeated adding, and knowing that you can get from one multiplication problem to another rather than start from scratch by adding or subtracting, subtracting the right things. A good place to start with multiplication is multiplying things by 2. Because when you multiply something by 2, it's really just like adding that thing to itself. 7 times 2 is the same thing as 7 plus 7. And a lot of cultures have developed their entire math around being good at like doubling things. And it's fun to just take a number like 1 and double it to become 2, and double that to become 4, and double that to become 8, and double that to become 16. Once you start getting a 2-digit number, it gets a little harder to double something. You could double 16 by doing 16 plus 16. That's one way. Doubling 32 is pretty easy because each thing, when I double them individually, they stay less than 10. Doubling 64, if you think of 64 as 60 plus 4, and if you double each of the pieces, it would be 120 plus 8, which is 128. Anyway, doubling is just adding the number to itself, but doubling is an important skill, and you can start at like a different number, like start at 3, and start doubling. And as long as, when you, like at this point, so far it hasn't been, I've been able to double 12 to get 24 and 24 to get 48. But to double 48, you could double the 40 and the 8 separately. So when you double the 40, you get 80. And when you double the 8, you get 16. When you put those together, you get the 96. Well, doing something like this is suggesting an important concept in math that's called the distributive property. And I don't think it's so important to know the names of a lot of these things. Like I see them teaching in elementary school, different vocabulary that maybe isn't so important. But let me tell you what the distributive property basically says. It says that if I want to do something like 7 times 8, I could do it in parts. I could do like 2 times 8 and 5 times 8 separately, and I'll get the same answer. You could check it. 2 times 8 is 16, 5 times 8 is 40, and it adds up to 56, which is what 7 times 8 is. Maybe we start the other way around. 2 times 8 plus 5 times 8 is going to be 7 times 8. This is an important idea. Sometimes they write it like this. 8 times 5 plus 2 is 8 times 5 plus 8 times 2. But this can be visualized pretty easily with, remember this, the grid, this rectangle picture? Here's a visualization. So 6 times 5 plus 6 times 3. Well, if I think of 6 times 5 as rows of 6 circles, and there are 5 rows like that, and 6 times 3 is 3 rows of 6 circles. Well, whether or not I know what any of these numbers are, it's not surprising that it ends up becoming a big rectangle, which each row has 6 things in it, but the height of that rectangle is 8. Even if I don't know what any of these 3 things equal, it's going to be true that 6 times 5 plus 6 times 3 is going to be 6 times 8. The reason this is an important thing in math, I mean, it comes up in algebra a lot, but even at this early level, when you do something like 48 times 2, and yes, you could do 48 plus 48 equals 96. Or if you're really good at doubling stuff, you're kind of thinking of it as 40 plus 8 times 2. In other words, you're doing 40 times 2, and you're doing 8 times 2. 80 plus 16 equals 96. So you're doing a little bit of like this distributor property, the idea that if I want to know 48 times 2, I could do 40 times 2 and 8 times 2 separately, and then combine the answers, and that will be the same thing as 48 times 2. Third grade seems to be the time that the times tables gets introduced. And it's great to learn the times tables. I know some people say, well, they're going to have calculators, so who really needs the times table? But the times tables are really a good opportunity. Now, I think some useful things to know in the times tables. I mean, we want to learn all of them. But it's good to mess around with, like, it's not quite doubling, but multiplying something by itself. These are good ones to know well. They come in handy, especially later on in math. 16, 25, 36, 49. I like those 10. Those are really good facts to have, and they're good to quiz students on. But yes, you want to know the entire times tables. Now, the 5 times tables, I think, is an important one. You notice that in the 5 times tables, every other number has a 0 at the end. Right, this is 5 times 1. Here's the rest of them. A thing to think about is, why is it that every other one ends in 0? Notice how the thing I'm multiplying by is even. Whoops, not that one. But these are. And hopefully they get the idea that if you group 2 5s together, they become 10. So if I have pairs of 5s, I'm going to be adding up a bunch of 10s. When you add up a bunch of 10s, you get 10s. But when the thing you're multiplying by is an odd number, you end up with an extra 5. They don't pair up. There's pairs and then there's an extra 5, and that's why you get a 5 at the end. Now when you take something like 5 times 6, if we think of it as, okay, there's a bunch of pairs of 10s because 6 is an even number, well, how many pairs are there? Well, for that, you get your most basic type of division, which is dividing by 2, otherwise known as halving something. Remember I mentioned before that I think doubling is an important skill. And when students get good at doubling, the numbers 1 through 9, which is basically the 2 times tables, but when they get good enough at it, the reverse thing is halving. If you take something like 48 and you want to take half of it, well, the 4 is like 40, and this is kind of like half of 40 plus 8. And remember I mentioned about distributor property? If you could take half of 40 and half of 8 separately and then put them together, you get your answer. So you can have things, if you have like 48, the 4 and the 8, you can take half of both of them, but you can't do that as well. If I say what's half of 96, it's not as easy to take half of that because the 9 is an odd number. But it's still an interesting question, half of 96. You could think of it as half of 80 plus 16, because 8 is even, and I can take half of 80 and half of 16 to get 40 plus 8, which is 48. And I just wanted to show you, that's kind of like, if you're thinking of it in that way, you're doing a little bit of a distributive property thing. Officially, that distributive property, the official way of saying it is that, like, usually they say it this way, like 5, or I'll say 8, like I had right here. 8 times 5 plus 2 is 8 times 5 plus 8 times 2. So this would be like half of 80 plus 16 is half of 80. In higher math, we use a dot there instead of a multiplication symbol, plus half of 16. If there's a fraction, you don't even have to put anything in there. I'm not done with half of 96 yet. I just want to say one more thing about that. "96 is very close to the number 100, so I could say half of 100 minus 4. And that distributor property works there also. I could do half of 100 minus half of 4, which is 50 minus 2, which is also 48. I'm not suggesting that your elementary school third grader thinks of the distributor property, but I think just this idea that some things that maybe you don't know can be solved by relating it to things that you do know. That's a big concept in math. You have some kind of problem that's really difficult, but there's easier problems that you do know how to do, but those problems like come together to solve your original problem. Anyway, this whole talk about halves came from here. To do 5 times 6, you want to know, well, it's a bunch of pairs of 5s. But how many pairs? Well, that's half of 6. Half of 6 is 3. 5 times 6 is the same thing as 10 times 3, which is 30. Now, if you know some of the times tables, like I said before, if you're really good with 7 times 6 is 42, but you forgot, what's 7 times 8? Well, 7 times 8 is the same thing as 7 times 6 plus 7 times 2. So you can add on 14 to 42 and get the 56. That's where little distributor property thing going on here. I'm thinking of 8 as 6 plus 2. But from the elementary school point of view, it's like, okay, I know what 6 7s are, but I don't know what 8 7s are, so what do I need? Well, I need 2 more 7s. And that way you can kind of get from one times table. And you're thinking mathematically. This idea in math of here's something I do know, and how could I use the thing I do know to get the thing I don't know with as little work as possible. Because you don't have to start over to do 7 times 8 if you already know that 7 times 6 is 42. Now, in 3rd grade, maybe they start getting into things like, you ask how many hours are there in a week? Well, to do 24 times 7, you could do 20 times 7 and then do 4 times 7. 20 times 7 is 140. If you know your 7 times 2 is 14, and 4 times 7 is 28. So there's 168 hours in a week. But look at the standard multiplication algorithm. You do 4 times 7 is 28. Imagine if I literally wrote like that. And then this 2 is not really 2, it's really 20. So 20 times 7 is 140. And I get the 168 like that. But that's not the standard algorithm. Usually what they do is this. 4 times 7 is 28. They put the 2 here. They put the 8 there, sorry. They put a little tiny 2 up here. Then they do 2 times 7 is 14, plus this 2 is 16. And they get that answer. But really, this is just a shorthand for this. That's really what's happening. You're doing 20 times 7, and you're doing 4 times 7, and you're adding the 2 numbers together. That's what the standard multiplication algorithm is. This 2 right here is the same as that 2 right there. I feel like doing another one of those now. 37 times 6. So I could do, if I do the 7 times 6 first, and then the 30 times 6, that would be more like the order that you're used to. So 7 times 6 is 42, but 30 times 6 is 180, and together we get 222. But the standard way of doing this is 7 times 6 is 42, put the little 4 over here. That 4 is the same as this 4. And then when I do 3 times 6 is 18 plus 4 is 22. That 22 is what I got when I added together this 4 with this 18. People memorize the multiplication algorithm with, where'd my little 4 go? Oh, sorry, didn't need one on this. People memorize that. I feel like this is the thing in math where a lot of students for the first time just sort of give up. like they don't really understand what's going on anymore. They just memorize, oh, I put this little 4 up here. But I hope when you see it here and you see how it's related to the distributive property, that 37 times 6 is the same thing as 30 times 6 plus 7 times 6, or 7 times 6 plus 30 times 6. When you get to more complicated things, like 24 times 53, it's really 24 times 3 plus 24 times 50, because 53. So I could do this. I could do this by saying, okay, well, 24 times 3, that's 72. I'll put that right here. And to do 24 times 50, well, I could just do 24 times 5 and then multiply that answer by 10. So 24 times 5 is 120. So 24 times 50 is 1,200. So that's the 24 times 3. This is the 24 times 50. Then you add them together. You get 1272. But usually you don't see these lines, this line and this line. They go this way. Nowadays in 3rd grade, they're not even doing this big multiplication algorithm, multiple digits. They're saving that, I think, till 4th grade. But I did want to mention, so this is what we do nowadays. 4 times 3 is 12. Put the 2 here and the 1 there. 2 times 3 is 6, plus the 1 is 7. But see how that's 72? That's the same as this 72 or this 72. Then they put a 0 here, or sometimes just leave a space, but I like to put a 0. And that 0 is the 0 that came from the fact that it's 24 times 50, not 24 times 5. So whatever ended up happening here, we were going to need an extra 0 at the end to make it not 24 times 5, but 24 times 50. Then they do 4 times 5 is 20. Carry the 1. This 1 we don't need anymore. 2 times 5. Oops, I meant carry the 2. 2 times 5 is 10. Plus 2 is 12. Notice that those are the same numbers as over here. And when I add them together, I get 1272. So this, I hope, explains a little more how this multiplication algorithm, the famous one, the one you learned when you were a kid with the 0 here and the little carries, it's really a consequence of splitting up the 53 into 50 and 3 and doing those two questions separately. 24 times 3 gave me the 72, and 24 times 5 led me to 24 times 50, gave me this. So this is 24 times 3, this is 24 times 50, and then all together is 24. I'll write it down like this. So this piece here was the 24 times 50, and this piece here was the 24 times 3, and then together is 24 times 53. Again, the distributor property says that 24 times 50 plus 3 is the same thing as 24 times 50 plus 24 times 3. Well, that's this 35-minute video about the ins and outs of subtraction. In the next video, I'll look at division. And I'm going to work my way up through all the topics. And this video series will not end until trigonometry, which is what most students learn in 11th grade, or if they're accelerated, they learn in 10th grade. I expect that this video series will be 25 parts, so it will be good 12, 13 hours of content. I'll be very impressed if people watch it all, but I'm really trying to do kindergarten through 11th grade, which is 12 years of math. So 1 hour on average for each year. Well, if you're still watching, that's great. If you have any questions, be sure to put some comments in. Thank you.